This section is an introduction to organometallic chemistry, which is really metals bonded directly to a carbon. And we'll see that the chemistry differs in several ways, but since the bonding to these soft ligands, carbons, are very strong, we can also take advantage of that to make some predictions about which formulas might be stable, something we couldn't really do with other kinds of ligands. Organometallic chemistry is a pretty young branch of the field. Its first organometallic compound was discovered. Of course, nobody knew what it was, but it was Zesus salt in 1827. This has an ethylene group, you see, pi bonded into a platinum center. We'll see that kind of bonding in a bit. In the late 1800s, there were other compounds, including nickel tetracarbonyl, which turned out to be a very important way to purify metals. And then really the field developed on its own with the discovery of ferrocene in 1956. And so the X-ray crystal diffraction pattern of this compound was really surprising, showing this so-called sandwich structure of these two cyclopentadiene rings attached simultaneously to iron. And this really drove a lot of new chemistry in the discovery of this kind of bonding and others. So there are, of course, an infinite number of organic compounds, but here's some common motifs in ligands for organometallic compounds. We've talked quite a lot about carbonyl ligands already. It's an excellent pi acceptor ligand, for example. But there's lots of other ways to attach carbon to a metal. So, carbenes have essentially a lone pair on a carbon, which are donating through a double bond to the metal. There's carbines. You can see the nomenclature here follows organic chemistry. There's also many cyclic ligands that can bond in a pi fashion. So here's the cyclopentadiene ring that we just saw on ferrocene. But you can have 3, 4, 5, 6 membered rings, so benzene can bond through all 6 of its pi electrons, and we'll learn how to count that up. Even some more exotic things like this cyclooctadiene and others. So here's ethylene. Again, we're thinking of this bonding through this pi bond in a side-to-side fashion mainly. Acetylene can also work the same way. And then there's other sorts of resonating pi groups like this allyl group. Yeah, so this is just a little taste of what's possible, and we're going to learn the bonding modes. So something we have to talk about early here is how to count the number of electrons which are bound to a metal. And so that uses this special phrase hapticity. So hapticity is essentially a count of the number of electrons which are donated into the metal. So here is an example of an ethylene group donating 2 electrons into a metal. And so the nomenclature here is eta. Eta 2 indicates 2 electrons from that metal, or from that ligand bonding into the metal. So here's an example of a larger molecule, right? So this is now propene, which is using its double bond here to bond to the metal through an eta 2 fashion, right? So both of these pi electrons are donating into the metal. It's possible to have a deprotonated propene to bond in what's called an eta 3 fashion, right? And so now we have these 2 pi electrons plus the remaining additional electron here from the deprotonated form. So this is anionic, so it's got 1 extra electron. All 3 of these would then simultaneously bond to the metal at once, right? Here's a butadiene group with 2 double bonds. Of course, all of these are in 1 pi structure, but those are donating all 4 of those electrons into the metal, eta 4, etc. So here's eta 5, that sandwich compound again, cyclopentadiene, which is really an anion. It's got a -1 charge. And we'll see that influences the number of electrons that donate in. So an important thing that we need to deal with when we're thinking about organometallic compounds is electron counting. And this is something we never paid any attention to for other metal complexes because the bonding really wasn't strong enough to be, to set any particular rules. Now, there's an analogy, which is the octet rule in main group chemistry. And this octet rule is there to balance the number of electrons to basically complete the valence shell for any element. And we could imagine that that's what's happening here as well. So metals have not only the s and the p orbitals, but also the d orbitals, right? And so they have a total of 10 electrons in those d orbitals added to the 8 from the main group, leading us to 18 electrons. But there's something else happening here as well, which is that we know that transition metals in an octahedral configuration have T2G and EG orbitals, right? If we were to fill up 12 electrons down here from the ligands, remember 2 from each ligand times 6, those all fill bonding orbitals, plus these remaining 6 electrons, that ends up being 18 electrons. And that's another way to think about what's happening here, is it's filling up all of the low-lying orbitals at once. We'll see that this way of thinking about it also matches what we'll see for square planar complexes, in which the favored rule is 16 electrons. So the method to count the 18 electrons that each complex has is we have to have a way to count up all the electrons. We have to add them. And there's two different methods. We're going to use what's in this textbook is called method A, but essentially this builds in the oxidation state of the metal. We count that in. It's something we need to pay attention to anyway, because a lot of things we saw depend on that oxidation state. So I like this method better. So first of all, we start with all of the electrons the metal owns, and you count everything, right? So if it's, sometimes these metals are in a neutral oxidation state. So iron 0, for example, it's in group 8, so it has 2 s electrons and 6 d electrons, and its number is 8. Okay, so we'll see. We'll work on that. So don't forget the oxidation state. That does change the number of electrons on the metal. So these two are tied together. Most ligands in this method are basically 2 electron donors. They have a pair of electrons that they donate into the metal. They may or may not be involved with pi bonding, but that doesn't change this count. Okay, this method is simple in that way, in that most ligands work the same way. But other ligands may donate more. For example, that cyclopentadienyl anion donates 6 electrons, we'll see. So that's because it's using more than one sort of pair of electrons to bond. And you can ignore the charge of the complex when you're counting these electrons, because the charge is built into the oxidation state of the metal, right? Oxidation state of the metal sets the charge of the complex. Here's an example of a whole bunch of ligands, and remember this method A is what we're using here, so you can ignore this last line over here. This won't be used by us, but it's another way to count. So this line shows that most ligands donate 2 electrons. All of these are all relatively simple ligands with one bonding atom. So that includes, pi acceptors like carbon monoxide, sigma donors, pi donors, right? Everything is in here. Most ligands are 2 electrons, so it's quite simple to count. The rare ligands that do form multiple bonds will form multiples of 2, right? So a pair of electrons from each of these bonds from an oxide or a sulfide in this way. These are not s-2, right? Okay, this is a sulfur using both of its electrons to bond. So the ligands that have multiple modes of hapticity, we have to be more careful with. Okay, so this A3 C3H5, that's the allyl group, but it's this, right? So this would be one of the resonance forms of that allyl group. And so what it's using is both of these electrons, a pi bond and then this lone pair in addition. Okay, that would be the way that we count that to the metal. So that's a 4 electron donor by this method. Let's look at benzene here. This is the same idea. Okay, so the benzene has, of course, a resonating structure with 3 double bonds in any one of its resonance structures, right? So if our metal is binding to benzene with all of these electrons, and that's why it's A6 down here, okay, that would be a 6 electron donor. We'll see there's other ways to bond in there that will change that electron count. Cyclopentadiene we've seen a couple times, so its count is 6, right, even though there's only 5 carbons, and you might ask why that is. That's because the molecule that's actually binding is the anion form like this, okay? Similar to the allyl group over there. So it's got 2 pi sets, right? Those are 2 electrons plus the other 2 from the lone pair. That's 6 electron donor. So let's practice some counting examples. So the first of them is ferrocene itself. Let's see what happens here. And so the 18 electron rule essentially predicts stable structures. So you would guess that a structure is stable if it follows the 18 electron rule, and if it doesn't, you'd expect it to be, easily oxidized or reduced, whatever it would take to get to that 18 electron count. You can have structures that so-called, that break that rule, but it is expected that the most stable form of them will be set to that count. So this is the abbreviation for cyclopentadiene. So we have 2 of those rings, just as we drew before, bonded into the iron. You'll notice there's no charge here, so this is overall neutral. But cyclopentadiene itself carries a -1 charge. So these are contributing a -2 charge, meaning our iron is +2. So iron 2, if you add it up, is a D6 metal. So we have 6 electrons from the iron, okay? We have 2 cyclopentadiene ligands, each contributing, as we saw before, 2, 4, 6 electrons, right? So when we add those up, we get 18 electrons. That's the rule, okay? Let's try this chromium carbonyl compound. Now notice there's again no charge here. Didn't forget it, it's just not here. So this is chromium 0, and that's okay. We'll see we can even have negative oxidation states with organometallic compounds. They're just in a more reduced state than you'd normally find in these more ionic-like structures we've been talking about before. So chromium 0 just has 6 electrons. That's its group number, okay? It's a mixture of S and D electrons. Who cares? We're about to add them all up anyway. So carbonyl is a classic, pi acceptor ligand, but it's a 2 electron donor. It donates through, in this case, these electrons on the carbon. So we have 2 electrons per carbonyl. There are 6 of those, so we have 12 and 6 again is 18 electrons. That's how we count. Let's look at some more. So here's a more complicated formula. This is iron with a cyclopentadienyl anion, and also in 2 different forms, an eta-5 and an eta-3. Okay, and we're going to have to think about what this means. We'll have to draw it out. And then also a carbonyl. So let's figure out what we know first. The carbonyl is definitely 2 electrons, no worries. What's the oxidation state of iron? Well, this cyclopentadiene ligand is -1, and it turns out that this eta-3 form is also -1. So that means iron, since the overall charge is 0, iron has to be +2. So it's again a D6 metal, so we have 6 electrons in our iron. All right, we saw before cyclopentadiene contributes 6, and so what's happening with this C5H5 in the eta-3 configuration? Well, if we draw the structure out, the way you get to 3 is the anion form plus any pi bond, okay? So if I redraw that kind of in the way that it would bond to the metal, we're going to have this resonating structure bonded to the metal, and then the other pi bond is locked over here, okay? So it's basically the -1 charge resonating between this point and this point. So that's 4 electrons. You could say it's 2 from the lone pair, if you want to count it as a localized form, plus 2 from the pi, okay? 4 electrons. Eta just tells you the number of atoms that are bound, right? You have to count the electrons based on the charge, perhaps. So it's basically the -1 charge added to the 3 atoms that are bound. Okay, so 6 plus 6, 12, plus 4 is 16, plus 2 is 18. All right, one more here. So carbonyls are simple 2 electron donors. We'll deal with cobalt here in a bit, but this is 2 times 3, 6 electrons. Here's a triphenylphosphine ligand. That's just a phosphorus with a 2 electron donor pair, right? So that's 2 more. What's the oxidation state of our cobalt? Well, these are neutral. Carbonyl is neutral. Triphenylphosphine, like ammonia, is neutral. So here's the charge of the compound, -1. That must be applied to the cobalt. This is a cobalt anion. Okay, so cobalt would normally have, it's in group 9, so this has 10 electrons. It's really a D10, it's not really D10, maybe it is. It's an SD combination 10 electron metal. So 10 electrons in the cobalt plus the 8 from our ligands gives us 18 electrons. We can solve little puzzles this way as well by counting. We're basically just seeing what it would take to satisfy the octet rule. So let's try this with a titanium carbonyl compound. So carbonyls are always 2 electron donors by this counting method. So we have 12 electrons here. We know that the metal must be balancing this out to give us 18 electrons, right? So this has to be 6. And the question is, how does titanium generate 6 electrons, right? So titanium is in group 4 normally. And so what does it take to get to 6? Well, we have to add 2 electrons in. And that would happen if titanium is actually -2. Here's another negative oxidation state. This is a dramatic example, but this compound is known. It's been studied. So the overall charge is -2. It's this charge carried over into the complex because carbonyl is neutral. Okay, let's try another one of these. We're just basically figuring out what the metal has to contribute to get to 18 electrons. So let's start with the ligands here. So we've got 2 times 4 is 8 electrons from the carbonyls plus another pair of 2 electron donors, chloride. Again, it's anionic, but it doesn't matter. It's still a 2 electron donor, so this is 4 more. So we got 12 here. We again need 6 electrons from our cobalt. We have to be a little bit careful because chloride is already charged, so we have a -2 charge here, but that actually doesn't change this number we're about to figure out. So what's the oxidation of cobalt to give us D6? Well, that's cobalt 3, right? Cobalt group 9 would have to lose 3 electrons to give us the 6 we need to get to 18 electrons. So if cobalt was +3 and the chloride is -2, then the overall charge of our complex here is +1. Okay, that's the answer to this question. That's the charge of the complex. Not really the charge of the metal, but the charge of the complex is what we're interested in. One more type of puzzle we can solve using this electron counting rule is predicting what metal would be stable in a certain complex, knowing its charge and its formula. So this is basically finding, and we'll assume here we're talking about a row 4 or a first group row transition metal. Okay. So we have 12 electrons from our 6 2-electron donor ligands. We have a +1 charge overall. But we do know that this metal here must be contributing 6 electrons. And so the question is, what metal is D6 with a +1 charge? Because this metal's charge carries over to that overall charge, right? So that would be a group 7 metal, and so this would be manganese +1. Okay, that's the name, that's the identity of this metal in this complex. So let's try another one with some more complicated examples. I should have specified the hapticity of this benzene here, so we'll assume that this is eta-6. This will be our assumption for these ligands unless you're told otherwise, but we'll try to specify it most of the time. So it's an eta-6 aromatic ring. You know, if you need to, you can always draw these things out and figure out how they work. So that's 2, 4, 6 electrons from each of those pi bonds. These methynes, these methyl anions are also just 2 electron donors. So there's 4 more from the pair of those. So we have 10 electrons here. We must have 8 electrons on our metal, right? So let's figure out what the charge of the metal is in order to figure out the number of its identity. So we have to be careful again. We have an overall charge of -1. The methyl groups are -1 each. Okay. So one of these is canceled by the metal to give us an overall -1 charge, right? Or you could say these methyl groups are -2, the metal is +1, and you add those together to get the overall charge of the compound. So this is metal +1, okay? So our metal +1 has 8 electrons. And so what metal must that be? Well, it must be the group 9 electron. It must be the group 9 metal, which is cobalt, okay? Cobalt +1 has 8 electrons. Okay.